share the right screen. There you go. All right, so as Jason mentioned, thank you very much. I'm Frikkie Enslin from Multotec. Some of you might think I put the mul in Multotec, but that's also okay. Hopefully my presentation today is going to be whole grain. Apparently whole grain bread is good for you, so hopefully the whole grain presentation will be nice as well. So today specifically I will be looking at dense media cyclones and why you shouldn't underestimate them at all. So first of all, I'm going to have a brief condensed look at the history of the cyclone, the DMS cyclone, where it developed and how it came to what we have today. Then I'm going to have a look at some factors influencing our dense medium cyclone efficiency. And then obviously we're all here to make money at the end of the day, is what's the financial implications. And then you'll see in my presentation with the Olympics being next year, there's a lot of references to Olympic sports and whatnot, just to bring it a little bit home closer. I'll have a final word at the end of the presentation, and then also I'm in the business of trading as well, so keep an eye out for these green tables all over the show with some important parameters and stuff you can take home and apply in the field. So first of all, our story starts in 1858 with Mr. Henry Bessemer. Now, when his modeling career didn't take off as he expected for some unknown reason, he think, why not try my hand at the dark arts of science? So Henry Bessemer's patent covered the use of chlorides of iron, manganese, barium, calcium as a medium, but there wasn't really any serious industrial application until the 20th century. So in 1891, a 43-year-old Bretney was the guy's name. Let me just quickly get my notes right. A 43-year-old Eugene Bretney filed a patent for a water purifier that looks much similar that we know today as a hydrocyclone. And the deal with this thing was to separate basically sand from water. And we can see that it's an early ancestor of our modern hydrocyclone or DMS cyclone. And then in 1911, the chance process patent was covered, and it used the sand and water medium in a cone separator. And in 1921, the first commercial plant using the chance separating process was used in cleaning anthracite. And then in 1922, there was experiments with magnetite medium for coal cleaning. And in 1937, was a good year, the Tromp process was first to use magnetite commercially. All right. So in 1940, there was the first US FESI patent, and also in the same year, Destiny decided to intervene. She said, listen, you boys, you're in the wrong direction. So what happened is, at the Dutch state mines, they were running shallow bath dense medium plants. And for cleaning coal using loose, which is a type of clay. And this was thickened in a cyclone. Now, when this cyclone blocked, it was noticed that the overflow pipe was full of clean coal, suggesting that somehow the thickening cyclone was concentrating the coal. Now, this observation led to further investigation and ultimately the development of the pretty dense medium cyclone as we know it by today. So in the mid-1940s, the guys started using dense medium cyclones to wash raw coal, and then the main evolution since then was basically in terms of size, but we still use the Dutch state mines as a reference for most of the cyclones that we see in the plants today. So if we want to move over to optimal performance, we basically divided it in 4 quadrants also, which you will require to get to that optimal performance. The first one would be obviously the cyclone design. Now, as I alluded in the previous slide, there was a lot of time, effort and money spent on what we have today and what we see in the cyclone as it is in the field. Secondly, we have to have a look at the ore characteristics. That also plays an important role. Obviously, dense medium, we'll have to have a look at the medium characteristics. And then finally, plant operation as well. Now, if we look at cyclone design, here we look at the physical cyclone ratios and dimensions and whatnot. And if it comes to the ore characteristics, we need to know about feed, particle size distribution, your washability, your near density material, etc. On the medium, in our case magnetite, we need to know medium to ore ratios, where do you need to be operating to be healthy, and then some medium qualities as well. And then obviously in the plant operation, we talk a little bit, or I'm going to talk in this presentation a little bit about your feed head, wear and maintenance, etc. Alright, so if we kick this off, and if we look at the cyclone design, and then typically the physical cyclone ratios and dimensions, the first very important one is your cyclone diameter of size. Now this is an influence on the cyclone's capacity. This means the total volumetric flow that you can push through the cyclone. And this is the wall-to-wall distance inside the cylindrical portion of your cyclone. So if we talk about a 900 cyclone, it means that measurement from wall to wall on the cylindrical section of your cyclone is going to be 900 millimeters. These days it goes up to 1.5 meters. Furthermore, if we look at our inlet dimensions, now I just need to clarify here, if I talk about inlet dimensions, I'm not referring to the square to round or your transformation piece. I'm talking about this physical inlet of your cyclone, because this is the constraint that your particles will see before entering your cyclone. So that is a very important aspect as well, because this influences the top size particles that you are able to feed into your cyclone. Now there's a rule of thumb, so your top size to your opening should be about 1 to 3. So that means if you have a square inlet like that, in this case let's say it's 90 millimeters, you can fit 3 particles in there. Those particles will be 30 millimeters. I would suggest then, as an OEM, that you don't feed the cyclone particles bigger than 30 millimeters. Great. So moving on. Your vortex finder diameter. Now this influences the maximum capacity to your overflow, which in our case in the coal industry is quite important, seeing that this is where our product comes from. So if we talk about our vortex finder size, once again we refer to the internal diameter. Spigot diameter, this has an influence on the maximum capacity to your underflow. Alright, you don't want to see stuff like that. Obviously if there's going to be a restriction, you're going to, traveling from Pretoria this morning, you see the taxis going over the yellow shoulder. Same is going to happen. If there's going to be a restriction in your spigot, your big particles or your heavier particles, which is your nonsense in this case, is going to report to your overflow, which is your product. You don't want that. It's worthwhile every now and then to bend the knees, have a look at the cyclone, have a look at the spigot and see if everything is still kosher. Then very important, something that gets neglected a lot of times is your spigot to vortex finder ratio. Now, once again, we like graphs, so there's a little bit of a graph, but I'll show it a little bit later on in the presentation as well, showing the spigot to vortex finder ratio and the effect it has on the expected efficiency on your cyclone. So first of all, if we sum up then for cyclone design, you can see that cyclone parameters in the original Dutch state mines, it ranges from 200 to 750 millimeters in diameter, and as mentioned, these days we get up to 1.5 meters. Inlets were typical 20% of your cyclone diameter. These days it can go up to 30%. Your vortex finder diameter to your overflow diameter, so it's typically 215%, which is 43% of your cyclone diameter, but these days it can be anything from 42 to 50% of your cyclone diameter. And then your spigot diameter, maximum, we say it's a maximum of 85% of your vortex finder diameter. And these days, we look at 70 to 80%. Just to show you some pictures, on the left is some of the original drawings as per the Dutch State Mines Bible. And on the right-hand side is some of the more technical stuff that we have these days. Not a lot of differences, but we've come a long way. So from a hand-drawn sketch to a very sophisticated mathematical and CFD model, the DMS cyclone has come a very long way to the elegant, reliable, and effective piece of equipment that we know and trust today. Good. So a little bit of a bonus fact. So all the newbies in the plant, first of all, they will say, okay, so the DMS cyclone is the one that lies down because it's bigger, it's fatter, it's lazy, it lies down. And your hydrocyclones is the skinny ones, the smaller ones, and they stand upright. If that is how you want to remember it, it's okay, but let me give you some more substance to that theory. So, why are DMS cyclones actually installed near horizontal, at an inclined position? Now, if it was installed vertically, like its thinner cousins, the hydrocyclones, what would happen? You would see that gravity will pull the media down to slump around the spigot area, and that will pinch the inner air core. Remember, we are working here with DMS, so it's not just water, there's fine magnetite included as well. And then separation efficiency will be very sensitive to inlet pressure and medium viscosities, all right? Because you are pinching that air core now. Inclined installation is easier for the piping. Think about horizontal piping. There's a reduction in headroom requirements because this big massive cyclone don't have to stand upright now. It can be angled. And then with the inclined installation of your DMS cyclone, you get some sort of buffer for the variations that may appear in your feed to your cyclone. So that's why as soon as you install a cyclone at an inclined position, you make the spigot a little bit bigger. So you'll have a bigger air core, which relates to a little bit more stability. So your underflow product will be more stable as well. So there's just a schematic where I indicate firstly on the left what will happen if you install your cyclone perfectly horizontal. You'll see that when it comes and you have to stop the plant, all the material or particles inside the cyclone will actually roll back to the roof of your cyclone. If we install it, and remember a cyclone, a DMS cyclone's cone angle is typically 20 degrees. If you install it at 10 degrees to the horizontal, it means your bottom wall will be horizontal with your floor, and it means that when you have to drain the cyclone, it's also still going to be difficult. All the particles will just settle wherever they are inside the cyclone. So ultimately we suggest that you install it at about 15 degrees to your horizontal, so that when you flush the cyclone, when you switch off your plant, the pump, at least the material can flush out of your cyclone. Alright, so this is what we want to see when a cyclone is stopped correctly. This is not what we want to see if you stop a cyclone. Alright, this is not a coal mine, this is a diamond mine, which I'm not going to mention the name of, but you can just imagine now, after a whole days of maintenance, this media, how stuck that is. It's like cement. And this, in this case being a diamond mine as well, is a little bit frowned upon to climb in the cyclone because you can actually fit in the cyclone to go and clean it out. Okay, so hold on to your seats. We're going to do a little bit of mathematics, but it's a Thursday afternoon, so I'm not going to be too rough on you. So we know the two main forces acting on each and every particle inside your cyclone is your centrifugal force, pulling it to the outside walls of your cyclone, and your drag force, pulling the particles to the inner core of your cyclone. Okay, so there's the formulas for each. Don't worry too much about it. You can have a look at it afterwards. What I want to do is, I want to simplify it a little bit. Okay, so we take out velocity squared, we times it by the motion, the radius of the motion on both sides. And then we assume a particle of a perfect sphere. That means we know what the area is, we know what the volume is, and then your constant for your sphere we know as well. It's 0.5, just as an example. We plug all of this in, We know that mass is volume times density, and we can see there we stopped at mass, so we can plug it in there and we sit with something looking like this. All right. We further finalize it a little bit. We delete some of the stuff just to get it nice and neat. Okay, so this is where you can stop. We can relax now. This is where I want to zoom in a little bit. So keep that flashing formula in consideration. The left hand representing your centrifugal force, the right hand representing your drag force. So what will happen if we have bigger particles? So that means your radius of your particle will increase. That means you will have a higher centrifugal force. So bigger particles will have a higher tendency to report to the underflow. What will happen if you have heavier particles? That means the density of your particle increases. Same story applies. So there's a bigger tendency for these particles to report to your underflow because the centrifugal force is taking advantage of here. Heavier liquid or a denser medium. So now you increase the right hand side. So if your medium is denser, you have a higher tendency for particles to report to your overflow. What happens if you have a bigger cyclone diameter? So the rotation motion increases. Once again, the FD or your drag force increases. So the bigger the cyclone, the higher tendency to send more particles to your overflow. Okay, so here's some ore characteristics which I want you to take special note of, because this comes down to a very, very suspicious finding that we have in our field of work, and we call it our breakaway size. So there's efficiencies for different sizes of particles, for different cyclone sizes as well. The big solid blue line being your 1450 cyclone, and the small pink line as an example being your 420 cyclone. So you can see the bigger the cyclone, the sooner there's this exponential breakaway from this horizontal line. So on your y-axis you have your EPM, and remember, if we talk EPM in cyclones, the lower the better. So higher efficiencies means lower EPM values. So what we see here is that with your bigger cyclones, you start to lose efficiency on your smaller particles if you pass a certain particle size. It can still separate it, it's important to know that. It can still separate it, but not as efficient as some of the bigger particles. So this is why feed PSD is so important. You need to know what you send into your cyclone and what your cyclone size is. Now there's a formula to calculate breakaway size as an indication. Remember what I mentioned? Particles smaller than this will still separate, but a little bit less efficient. As an example, for a 900 ml cyclone, we see the breakaway size is in the order of 4.2 millimeters. This doesn't mean that you cannot send 3 millimeter particles in your 900 ml cyclone. Just keep it to a minimum. Okay, so washabilities. I see we're a little bit pressed for time, so I'm going to quickly go through it. So we make up different densities of liquids. We take a sample and then we do a float and sink analysis. So you drop it in one of the densities, it separates, and you continue on, so on and so forth until you get to the end. So what you do is all these different particles are now separated in terms of density. Then you take that sample and you go and analyze it, approximate analysis, CV, ash, yield, whatnot. And that is how we set up our washability curves. So this is typically what a washability graph may look like, with your purple line being your yield, and you read it on your y-axis, your primary y-axis. So you can see, remember what I said about the density of your liquid? If you increase your density, your yield will increase as well. All right? But with that, unfortunately, goes the quality of the coal as well. So if you increase your density, you will see that your ash will increase, your ash value will increase as well. Okay, now let's talk about medium to ore ratios, something that I think gets left out and left behind a lot of times on site because you can't quickly go and measure it with an instrument. You actually have to calculate it most of the time. Now, in the design of a dense medium cyclone, the volumetric flow rate to the unit is dictated by the solids feed rate and the volume of medium required for an efficient separation process. So for sufficient separation of the ore particles, one requires a certain volume of medium, which is in our case water and magnetite, per volume of ore being fed into the cyclone. So this is a volumes game. So if the cyclone is too congested, the particles can't move where it should be, so there is a specific ratio that we need to try and keep. So if your medium to ore ratio is too low, you will get overcrowding of ore solids, the loss of efficiency. If your medium to ore ratio is too high, you'll need a bigger piece of equipment, all right? More expensive, higher operating costs, increased medium losses, and then there's actually a very little effect in terms of improved efficiency past a certain point. Okay, so to bring this in perspective, here's my first Olympics example. So if we look at a swimmer in a swimming pool, I say the swimmer will be our ore particle, and then the water will be our medium. All right. Now, if we talk about medium to ore ratios, look at these three examples. All right. So if you are practicing for an Olympic event, you're a swimmer, which one of these three scenarios, the one on the left, the one in the middle, or the one on the right, do you think will be ideal for you to break that record? So I'll go through it. First of all, the one on the right, the medium to ore ratio is too low. There's too little medium for all the ore, and the color of that water seems a little bit dodgy as well. The medium to ore ratio on the left will be okay. There's no one interfering with you, but remember, now you're swimming, you don't have to have this big of a swimming pool, all right? So you're wasting some water and cement and whatnot. So over here is where your medium to ore ratio is within spec. Okay. So for coal, we're looking typically, South African coal, 3.5 to 4.5 to 1. This means that for every 1 cube of ore that you treat, you want 3.5 cubes of medium to go with it in your cyclone. For diamonds and other minerals, just as reference, there it is as well. So if we look at medium suspensions, so you typically get your homogeneous suspensions and then your heterogeneous suspensions. Homogeneous suspensions is your organic liquids and salt solutions and whatnot, which is lacquer because it's homogeneous, but unfortunately they tend to be carcinogenic and corrosive, so the people don't like to work with it as much. So with heterogeneous medium suspensions, we therefore look at water and a certain solid. So this can be anything from sand initially, galena, pyrite, and then magnetite and fezzi that we are more common with. Okay. Medium qualities. You can see this slide was prepared for a diamond mine. So let's say you feed your cyclone at a certain density. You'll see that your overflow density will be a little bit less than your feed density. Your underflow density will be higher than your feed density. But none of these three values that I'm showing you here is actually your cut point density. All right. Cut point density is one of those things, again, not very easy to measure somewhere with an instrument on site, because your cut point density is roughly around there, and in this case, let's say it's around 2.9. All right. So you have to go and calculate it. It's about a third from the bottom of the cyclone. So to determine whether your medium is actually healthy, there's actually medium differentials that you can go and calculate. And the one that is used most often is your feed to overflow medium differential. Overflow, why? Because if we think about the guys in the diamond fields as well, they are a little bit sensitive of you taking samples of the underflow of the DMS cyclones. So feed to overflow. And here we want a differential between 3 and 12%. So in this specific instance, you take then the density of your feed divided by the density of your overflow, and you work it out as a percentage of the density of your feed. And in this specific instance, it's 7.55%, It's like a smack bang in the middle of our suggested feed to overflow density, so you're happy with that. What happens with your medium characteristics or your medium qualities? Let's have a look at this model that I created over here. So on the left-hand side is a cut through in the vertical plane of your DMS cyclone, and then on the right-hand side on a horizontal plane of your cyclone. All right? So what will happen is, as soon as you feed medium into this cyclone, you will see that it will actually start to classify as well. Remember, it's still a cyclone, so it will still classify the product inside. So because a lot of the medium will report to your outer wall of your cyclone, you'll get that your higher density region will be on the outside, whereas your less dense regions will be in the center. Now, why is this important? Because if we feed a particle of a certain density, or let me just show you quickly there, indicated with red is your locus of zero vertical velocity. All right? So everything inside that circle is supposed to go up through your vortex finder. Everything outside that circle will go down to your spigot. So let's say we have a particle of 1.9 density. It will come in at one heck of a speed, and ultimately it will go and settle somewhere between the 1.8 and 2 density fraction, example over here. And it will report to your spigot. Let's say we have a lacquer sweet coal particle at a density of 1.3. It will find its way in the 1.3 density band, and then obviously report to your overflow as well. All right. So let's mess around with your medium to ore ratios. What will happen? So let's say your differential is too high. This means your medium is unstable. This means that your medium will classify too much. What will happen is it doesn't have an effect on your rejects. Your rejects will still report to your spigot. But now watch what happens with our sweet coal particle. This, unfortunately, will also report to your spigot and your rejects. And this is why it's so important to keep track of your medium to ore ratios. Now you can go and calculate it, or as we are engineers, we are relatively lazy, and that's perhaps why we like graphs as well. So here's a graph indicating your sweet spot or your healthy area. This is where you want to operate. This is your acceptable operating range, with your circulating medium density on your x-axis and your overflow density on your y-axis. So as an example, if you're above that acceptable operating range, you will sit with high viscosity. So there isn't really going to be any separation. And if you sit below that range, you sit with low stability, right? As per the previous example I showed. So if you measure your feed density and your overflow density, and you see your feed density is 1.65 and your overflow density is only 1.64, they meet each other outside this green lane, which means high viscosity. The other way around, if your feed density is 1.85 and your overflow density is 1.5, you'll see that they meet each other below this operating range, which means you'll sit with low stability. So ideally, I have to give you a good example as well. So 1.5 feed and a 1.4 overflow. Bob's your uncle, we can work like this. Your medium is healthy. Okay. Furthermore, to medium characteristics, like we have different athletes participating in different sports. In your Olympics, you have different medium or particles that can be used for different applications. Now the guys in the diamonds and or iron ore, there's different Fezzi types. I'm just showing it as an example over here. Milled, water atomized, gas atomized. So it's looking at the physical particle shape as well. On our side, in terms of magnetite, we just basically classify it in terms of the fineness. All right, fine, medium, coarse. All right, which all has its advantages and disadvantages. Now, plant feed operation. If we look at a feed head, now, if you have ever spoken to a cyclone's guy, you will know that they refer to the feed head of the cyclone in terms of the diameter of the cyclone, a certain D. And typically we want that feed head of a coal cyclone to be 9D. What does that mean? So if you have a cyclone fed from a tank, there's a certain head associated with that tank, and this causes a certain velocity of whatever is fed into that cyclone.